Hello everyone, welcome to Engineers Ireland. Today what we will be looking at is the section that's normally called the special question, the one that's in part B paper 2, the one on calculus, further calculus and series. Now I'm also, just to inform you, likely to cover at least one more question from that section in another week or two, so you won't be just depending on this one. Along with that, I would say to you that we're going to take a fair amount of time over this section. We'll spend, I think, 2 of these talks on it. And by the end of it, I would expect that you will have a very good understanding of it and that it shouldn't be something to be feared. The interesting thing is, because there are quite a few new concepts and interesting enough mathematics, what that basically means is that the questions are generally straightforward. You're expected to show in the questions that you understand the principles and the level of mathematics that it has. For example, if you look at geometry of the line, because the mathematics in it is quite simple, you can get very tricky questions in the exam. This generally isn't the case here. So then, there are basically 4 parts to this section. And we'll be looking at 2.5 of them now. The first part has to do with one last thing you need to know on integration. The second part has to do with an aspect of limits and series. It's got to do with whether or not a series will converge or will not converge. The third part has to do with the Maclaurin expansion that allows us approximate for series. And the fourth part then is applications, which has to do with, for example, being able to prove the volume of a sphere, things like that. So what's the integration bit? We have this equation. What we're basically saying is, if we have a product, a UV, a bit like we had in differential calculus, what can we do about it? Well, integration is a bit devoid of very good, useful tools. This is probably the nearest it comes to having something like a product or a quotient rule. Now then, we can arrive at this by looking at the product rule . We multiply across by the dx. So that's pretty obvious. And now we can say, remember, by the way, when you have got du's, that basically means a little bit, an infinitesimally small piece of something. So we're saying that the infinitesimally small piece of the product uv is equal to the u function by the small piece of the v function plus the v function by a small piece of the u function. So to find what the whole lot is, we can integrate both sides, get the full integral, and the integral is the sum of all the little bits. It's basically what's referred to as a Riemann sum, and you will find that out next year when you're in college. Okay, all that is pretty straightforward down to here, and all we've got to do now is swap one of the pieces across to the far side, and we come back to that equation, the one that we wanted. Now, if we have limits, you will find that the limits will apply in all three locations. And if we didn't have limits, you will find when you get an answer, you will have to add in the plus c, as you would in the other integration that you've covered already. Right then, what's the next thing that you need to know about this? We have to slightly mispronounce a word here, liate for late. This is the key word for using our new tool. If you remember, we have a u and a v bit, and the ways it's organized is the integral of u dv. And we have to hunt for something. What we want to hunt for is what is u? Because after all, we will be presented with a problem to solve, something that we need to integrate, and it'll look like this. And our first job will be to find out what is the u part of it. This here is a hierarchy. The further up the hierarchy, anything that's high up in this hierarchy will be taken as the u ahead of something that's further down the hierarchy. So let's have one quick look at this and we'll see what we mean. So we have two things. We have this thing and we have this thing, and one of them will be associated with the dx. So what we have to figure out is what is going to be u and what is going to be the du. Or sorry, the dv. Now, that's an algebraic expression. It's sitting there. This is an exponential. It's down here. So this is going to be our u. It's going to be the algebraic one, this one here. So we can say u is equal to 2x plus 1, and we can say that dv is equal to e to the x dx. Now, we're going to differentiate the u. And we'll have to integrate this side. The integral of dv, which happens to be v, is equal to the integral of e to the x dx. Now, we don't put in a plus c there. Okay, we have all the little bits we need now to populate out this equation up here. And in usual form we'll name the equation, because very often if you have to repeat it further down it will save you time. So the integral that we want, which is this one, is going to be equal to u v and down here we do use a constant. You can see the methodology that you've learnt already for integration is applied here. The only difference is we're going to be replacing the integral we were asked to deal with by two items. One is a simple product and the other one is a new integral. Certainly one of the books that I've seen actually swaps these two around, but all the rest of them keep them in this order. Okay, there's basically three more things you need to know about these. First off, what we just did there was the simple case. It's where one use of this rule is enough to allow us solve the problem. In other cases, the type we're coming on to now, you will need to do it twice, and you will actually notice that there is a certain pattern to it that makes life easier for you once you start to recognize what the pattern is. Let's look at this one. The x squared is algebraic, cos x is trigonometry, so it's going to be, this is going to be the u. Remember, no constant of integration here. And we can have called this thing here, we could have named it I. Now we've got what we require. We can say that implies I can be replaced by uv minus the integral of And this time you do know that we do have our limits. So we can say it's equal to x squared sine x going from 0 to pi over 2 minus the integral from 0 to pi over 2 of sine x by 2x dx. We still have a product here, and that's the whole point for this example. Now there is a difference though. Up here what we had, the algebraic part was an x squared. Down here the algebraic part is just a nice simple x. So we have made some progress, but what we have to do now is apply the exact same game again to this integral here. The x is still algebraic, so it becomes the u ahead of the sine x, which is trigonometric. It's that being further down on the Lie list here. So now what we can talk about is, I write it over here. So now our v is minus cos x, again with absolutely no constant added in here. So I can say all of this is equal to x squared sine x from 0 to pi over 2 minus 2 outside of, and now I'm going to play with the bits for this inside one. Now, well, I'll actually write it as it should be. And you can see that that minus and that minus will give us a plus. This is not going well here. Something that will make this a little bit easier for you will be when we get down to this level here, we can make the decision of giving this a name, and we could have called it, for example, I2, integral 2. We could have then set it, stepped aside and integrated that. And we'll follow that process in the next one, because what you will find is if we don't do that, you carry this and you keep carrying it all the way down. So here it is, the same thing written 4 times. What you will have noticed in this last one is we had started off with an x squared cos x. The next integral had an x sine x, and the last integral was a cos x. So what has happened is that we eroded down the algebraic one by the process that we applied here. X squared went to x, went to 1. Now that clearly means to us that if we had the integral of x cubed cos x, you would have had to repeat this process another time, and each time you would have been eroding down x cubed to x squared to x down to 1. You could obviously say if it was x to the 4 cos x, you'd have to do it 4 times. But no matter how you really think of these things, you know you'll get to the end of the number of these. There's a particular case though where it could go on forever, where you could keep having to apply this new rule and you get really no further. And there's a cute little trick that allows you to get out of that, and that is where you see where the thing actually starts to repeat itself. And it's the case where we've got the exponential multiplying into a trigonometric function. That's where these things happen. So in this particular example, that's further up on the list. There. It's further up than this guy, which is down here, so this one will be the u. So we can say u is equal to cos x. And if that was u, then dv must have been equal to e to the minus x dx. Now I just want to remind you that that minus here is important. It's e to the minus x, which technically is e to the minus 1 times x. So if you look at your standard integrals in your logbooks, you will find integrating e to the x is treated separately to e to the ax. This is an e to the ax example, and I know certainly a question came up in the Leaving Cert where it had, for example, e to the x minus e to the minus x, and I would consider that one of the ways that they were hoping to see if people aren't staying awake enough was in recognizing that minus, so that you do finish up with this guy out here. Notice again, there is no integration constant here. So now what can we say? Our integral here, this guy, is equal to minus e to the minus x multiplied by cos x minus the integral of minus e to the minus x Now I know we have a minus here, a minus here, and a minus here. And rather than trying to work it out in your head and saying minus by minus is plus, multiplied by minus is a minus, you're better off to parachute these things in with inside their own little spaces, with these shown by these brackets, and having written them down, then rationalize out your signs. we can call this equation any name we like. We'll just call it equation 1. Let I1 now be equal to this new integral. And we're saying to ourselves, it's a product. Which do I pick? This is the trigonometric one. It's higher up in the list. So we play the same game again. You will notice that this here was the same as what we had earlier. And when we integrate e to the minus x dx, we get minus e to the minus x. So then, we can say that implies that I1 can be replaced by and I'm making this one big. This thing here, isn't that what we started with? The integral of e to the minus x cos x. So I can replace this down here by the name that I gave to this one up here. So my I integral, and actually equation 1 becomes and this minus multiplying into the I means I have a minus I here, which I can pull over to the far side, so I can say 2I then is equal to do have your constant here. Well, I'll actually spare it for the last line. Do you notice that the actual integration you're doing here is simpler than many of the pieces of integration you had to do in the chapter on integration? That's because the emphasis here is on the new method, the being able to replace an integral by a product minus a different integral. And very often you'll notice in these questions that once you understand the methodology here, that it's much easier to get a mark out of this, or a good mark out of this, than it would be in a question in integration, because the actual, once you've got the process, the actual methodologies you're applying is going to be very easy. we've almost finished this integral part here that's in the special question. The last thing that these can be used with is this method can be used to find the integral of an inverse trig or a log. And the example that's provided here is a log one. It's pretty obvious now what our two items are. Pretty easy. And the good news is you'll generally get something to do with this integration in the question. Now for the next bit. This is where we add another little piece of understanding to how useful limits are. And it's also showing you why it's important to have studied the series and sequences chapter, because they come in here again, and you're expected to be able to apply basic understanding from that chapter in this special question. So it's very important when you're doing those to remember that you're also aiding your mark in the special question. What we're going to work on is something called the ratio test. If we have some series by the way, whenever you see a series written, always take particular note of this, the first one. This is saying it's a sum. Sigma means the sum. It's the sum for n equal to 1 up to infinity. In some cases it'll say n equal to 0, and there are a number of cases where it could be, for example, n equal to 5 up. But in this, generally for the Leaving Cert, it'll be, we'll say n equal to 0 or n equal to 1 starting. But watch it, because that's what's going to give you your first term. It's so easy to imagine that they all start with 1. The first term can be term 0, not just term 1. So we're saying, oops, that'll give me a first one. It's called 1 because that thing is 1. If that was n equal to 0, we would have b0 here now. Now, we want to find out this sum that will go on forever and ever, will it converge? For example, we know that 2 plus 4 plus 8 plus 16 plus 32 plus will not converge, that you will get even the last term itself will be an infinite one. It's more interesting to look at a half plus a quarter plus an eighth plus a 16th plus a 32nd and on, and find out, will that converge? The answer to that one is 1. So it has converged. And what you will notice is that the number underneath, like for example 1 over 8, the following is 1 over 16, the next one's 1 over 32. The number's getting bigger underneath, which means each term is smaller than the previous term. And as you head to infinity, the last term gets to 0. It becomes equivalent to nothing. What is our ratio test? R. It's the limit. As this n goes to infinity, we could have talked about over here there was a bn1, the next one was bn plus 1, and on and on. We're going to look at a term divided by the term that was just ahead of it. And we're going to look at that, and we're going to find the limit as n goes to infinity. What are the basic things we're supposed to look at in relation to r? The series converges when r is less than 1. It diverges, it does not converge. When you get an answer of 1, you can't say that it will or that it will not converge. It's just that the test fails. This is the only one of these type of tests that you have for the Leaving Cert. So you're getting a very useful tool to allow you actually simplify a lot of other mathematics. And it does work very, very nicely in the next part of this section where we're dealing with the Maclaurin series and things like that. But in the meantime, we're going to have a small number of examples that will get us used to using this ratio test. We want to use the ratio test now on this. So, when you see a series set up like this, where you've got the sum of something, this is always the general term. So we can say Bn and we also want to work out what's the next one. So any place you have an n here, you're going to be putting into that n plus 1. Now I've got a particular habit of doing this, and that is while I'm here in this stage rather than down working in the ratio equation, I always try to adapt the bn plus 1 to being as alike as it can be to the bn1. So 2 to the power of n plus 1, that's 2 to the power of n by 2 to the power of 1. So we now have n plus 1 all over 2 by 2 to the n. And we have found, we've made this look like that. So we've got our simplification already set up for the r equation. And we know if we're dividing something by a fraction, It's the same as multiplying by the reciprocal of the fraction. And now that is seen to cancel here. Now, something you need to know, you can see that we are using the absolute value signs here. Look at them. They're put in here because sometimes you actually get terms in there where there's a possibility of a number being negative. But we do know that from our very first equation that n starts at the number 1 and moves up the way, which means that at this point here I don't need to use the absolute values because I only have n inside and whole numbers that are greater than 0. So I could actually just drop it at this stage. Now, if you remember when we were dealing with the limit for an algebraic rational expression like this, one algebraic function divided by another, you find the highest power of n, and in this case it's just n to the 1, which is n, and you divide each of the terms by it. So we can say that implies r is the limit as n goes to infinity of 1 all over n of 1 plus 1 over n all over 2. We do know that the limit as n goes to infinity of 1 over n to any power is 0, which means this guy is going to disappear on us when we apply the limit. And we'll just have 1 over 2 as the answer. As r is less than 1, the series converges. Series converges. So we've proved the thing. This can be used to any type of series, including power series expansions, which is the type of thing we'll be moving on to very soon. That's why it's mentioned here in this section, in this sub part of the section. Now, there's a few things that you need to know. Let's say, for example, that when we are inside the absolute values, if you've got an expression in x or some variable, unless we've been absolutely told in the question that it can't be 0, unless it has, unless we're certain of it, we have to assume that it can be negative. For example, let's just say that we were looking at the limit as n goes to infinity of, we'll just say x by, well, we'll pick what we had a minute ago. Do you notice it's the n that's going to infinity, not the x? Even though x is a variable, it isn't being changed by the fact that we're moving through into higher and higher values of n. What that means is I can actually take the x outside, but be very careful because I only can take the absolute value of x outside. And now I have the limit as n goes to infinity of the 1 plus n all over 2n. And we do know that the n values inside here are only, for example, from 1 up. So we could drop these absolute values inside the limit. We can't always do it, but in this case we can. The important thing to remember, though, is if you're pulling out something like an x from an absolute value, that you have to keep the absolute value outside of on the x outside the limit. Here's one other thing. If the answer is r, the ratio is equal to 0, what it means is that it converges for all values of x, whatever the variable is in the function. So we're happy, especially if we're looking to find an approximation for some function where we will want to use the full range of values of x. It's very good to find a result such as r equal to 0. And clearly, if we look at this example up here, let's just show you how that would work out. We would find the ratio is equal to the absolute value of x by, and if we work out the limit here, we'll get a half. Now, what are the limits that we have? Basically, the limits, we're saying up to, but not including 1. So I could say minus 1 could be less than this here, which would be less than 1. Now, at this stage, because I have split it into the minus and the plus, I can do without these guys. And I can multiply across by 2, and I get minus 2 less than x less than 2. An example will be helpful on this. Now, the other thing you'll notice that we'll start to do is get to be quite careful on dealing with our general term and the term after it, and being able to manipulate the bigger one into something looking more like the smaller one, just to make your mathematics easier. Sigma n equals 1 up to infinity of x to the n all over that implies that the bn plus 1 is equal to x to the n plus 1 all over, and in here it is worth your while at times to do this, to put in the second bracket around this here so that we can fit in our numbers correctly. And we'll say to ourselves, that implies then that bn plus 1 is equal to x by x to the n. This is splitting the terms up in the bn plus 1 so as to find the parts that are like the bn1. And in here, what we had in this overall thing now is clearly and it is being multiplied by 2 to the n. So what we find is that bit and that bit are shared with the bn1. that cancels that, this cancels that. Now, from an ordinary mathematics viewpoint, there's no need to split up the answer here into two pieces, but we're doing it because we know when we're going to get into the ratio where we have a limit, we'll be able to pull out the things that haven't to do with n. And anything to do with n, such as all of this here, will have to stay inside. The 2 and the x are independent of how n changes, so they can be pulled out, but they have to, especially the x has to get held inside the absolute value there. And everything that's left over, all of this stuff, is just n bits, so we can remove the absolute value in here. Because that limit is 1. So we're able to say, so the absolute value of x over 2 needs to be less than 1 for the series to converge. Now we can expand this out and we say that implies minus 1 is less than x over 2, which is less than 1, which implies minus 2 is less than x, which is less than 2. We can now say that this series that we have here will converge only if the x value in it lies between minus 2 and 2, not inclusive. Obviously, your books will have a number of exercises on this. It is worth your while, actually, and well worth your while to practice it, because it's that practice will actually strengthen your ability in your limits elsewhere, and also for the parts that are coming up, particularly the Maclaurin series expansions. You need to turn what you understand into what you know, and there's only one way of doing that, and that is by practice. That's why these examples are so important, and the exercises that you have are really important. What we need to look at now, just before we move on to the Maclaurin series, is a form of shorthand. You will have been noticing, as we went through the maths course, that there have been quite a number of shorthands. For example, cos theta plus I sine theta was cis theta. Now we're coming to a new one, and it has to do with higher derivatives. If we have y is some function of x, we know already that dy dx is finding the slope of f. Okay, and we would have written before that's the d dx of f of x, and we'd have already called it this f dash at x. Similarly, Now it should be clear to you that after you get on to 3 little dashes, this becomes impractical. You can easily distinguish 3 dashes. If you had 4, 5 or 6 or more dashes, it could be difficult, and you finish up just having to count your way through them and hope that you wouldn't make a mistake. So we need a new way of identifying how many times the function f of x has been differentiated. And what we do is, we'll say, now you will notice all the way along here we're differentiating once, this is twice, this is 3 times. So now we're saying the nth differentiation and this is what we're doing. We're using this example it's very important you do not leave out these brackets, because if you left those brackets out, you'd have f to the power of 5. Okay, you'd have the function to the power of 5, and that's not what we mean here. When you see those 2 brackets with a number inside it, you're saying that this function x was differentiated that number of times. And by that token we can also state that the function itself, we could actually refer to it as f0 at x. It's just a little addition to the thing, it's not massively important. So we'll give ourselves an example. So you will see how this was brought in here. You now have all of the things you need in order to start into the Maclaurin series. And fundamentally, this guy noticed something very cute. If we have a power series, that if this function we're talking about can be replaced by a constant plus another constant by x, forever and ever, what's the use in that? What's the use in being able to give you an infinite number of numbers to replace something that's definitely finite? The only way it's useful is if the sum of that series here, for example, has a limit, that it tends to something, and also if a small number of these, 4 or 5 of them, could give you more than enough accuracy in your answer for what you require. But how do we actually make this into a very practical scenario? The good news is someone else did, a guy called McLaurin. And we're going to look at a series. Now I know I have drawn this many times before, but it's always worthwhile drawing it. This is a straight line, and we will use the lettering that we have here. That was the same as when we were writing. Well, we're just using the letters that he has. What you will notice is when x is 0, y is equal to u0. Okay? So I now actually have a way of working out this guy. We're saying f at 0 is equal to u0. Whatever the function is, put the value of x into it. Whatever you get as an answer is this first coefficient. Now we're trying to figure out the second guy. And where this guy got really cute is he realized if I differentiated once, I'll now be able to bring this guy out as a constant on its own. In other words, not multiplied by x. So let's see that. I'm now going to differentiate all of these guys up here. And you will say, well, clearly I'm going to get a nothing plus a u1 plus 2u2x plus 3u3x squared plus and on and on and on and on. And once again, what we will notice is that f dashed at 0. What is f dashed at 0? So now we have figured out this guy. Let's differentiate it again. There's no x left here. So we can say f double dashed at 0 is equal to 2u2, which implies u2 is equal to f double dashed 0 over 2. We can do it again. Now, if I put 0 in for x here, I'll get the free term again. So that implies u3 is equal to the f triple dashed at 0 all over 6. Look at the numbers that we have here. For the first one, we're able to say that I'll rewrite them actually down along here, just so as you can see it. The u0 is equal to f dashed at 0. Factorials. Let's look at factorial. For example, factorial 5 is equal to 5 by 4 by 3 by 2 by 1. We can also say that factorial 0, it's how many ways of picking nothing from nothing, is a 1. So life's getting nice and handy for us. Do you notice here that we are actually using our first term? It's called a U0, whereas when we were looking at the ratio test, we were talking about B1, B2. As mentioned back then, you can actually start off with a 0 value. So we can now say, let's pick this one here as a means of getting an understanding of how this thing will give us a general term. When it's U3, when it's this guy here, you have factorial 3, and you've got differentiated 3 times. So we should be able to say that the nth one is we're going to differentiate n times, put x equal to 0 n, and then we will divide by n factorial. This then will give us the famous Maclaurin series. Notice n equal to 0 because we have started with U0. We're going to play similar little tricks with this as we were playing in the ratio test. The nice thing is you only have 6 of these to work out for on your Leaving Cert course. 4 of them are relatively straightforward and 2 of them take a bit more attention. But because there's a definite and quite small number of them, it's well worth while learning how to do them. Exponential, you get the natural log, you'll get sine of x, you get cos of x, you'll get the binomial, and inverse tan. Exponential, natural log, sine and cos, binomial and inverse tan. Let's pick the easiest one to begin with. So, the Maclaurin series expansion of e to the x. We'll be able to populate up. Now, normally you do write in the general Maclaurin series, which is just the f at 0 plus f dashed at 0 by x plus f double dashed of 0 by x squared divided by factorial 2, but I'm running out of space. So we will say that implies e to the x is going to be 1 plus 1 by x plus and we just have to work out what our general term is. The easy way out of this, remember how you can always start with a term 0 or a term 1. Go over and find where there's kind of consistent or easy to deal with numbers, and say to yourself, if that was a 4, this was a 3, that was a 2, if this was a 1, in term names, it would make life easy for me. So I could say that's T1, T2, T3, T4. But I have an extra one here, so that's T0. So we could say that the nth term, if we look at this guy, we know the nth term. we can also say that e to the x is now equal to the sum as n goes from 0 up to infinity of x to the n all over n factorial. The next and obvious question does it converge? And you do understand we're only calling it Bn. We could say that that is the limit as n goes to infinity of Tn plus 1 all over Tn. You can call it Bn, you can call it Tn, you can call it Un. It makes very little difference. It's just a name. So then, we do know what Tn is. So, that would imply that Tn plus 1 is going to be equal to x to the n plus 1 divided by n plus 1 factorial. Now remember, just in case you needed reminding, 5 factorial is 5 by 4 by 3 by 2 by 1. 5 plus 1 factorial is equal to 5 plus 1 by 5 by 4 by 3 by 2 by 1. So it's equal to 5 plus 1 by 5 factorial. So I'm now in a position to be able to say this is n plus 1 by n factorial, and on top I've got x by x to the n. And what you will notice in this Tn term here, I've split it so that part of it is the Bn. So I can now say to you that implies Tn is equal to x all over n plus 1 by Tn plus 1 here, by the Tn1. So the ratio is the limit as n goes to infinity of and I am going to be dividing by just so as you're clear, I could have immediately hopped to this one based on what I've done up here. I would have x all over n plus 1 by Tn being divided by Tn, and you'd very quickly see that these cancel. And now we're left with this is the limit as n goes to infinity of x all over n plus 1. The x is not affected by n moving up, but it could be negative. So we have x, absolute value of it, and the limit as n goes to infinity. Now inside here we only have the n plus 1, and I don't need to put the absolute values around that. And when I get the limit of this, just to do it out the long way for you, of 1 all over n all over 1 plus 1 over n. In the limit, that bit will go to 0 and that bit will go to 0. series converges for all values of n. So that's very useful. We have found an expansion that represents e to the x, and no matter what x value we use, this series converges. There's a little example here, and it's actually worth noting it, and I don't mean just particularly for this case we're looking at here, but as we move on, and especially move up to the inverse tan one, where we're looking at estimating pi, there is something that can get gleaned out from each of these. So let's just look to begin with and say, what about getting an estimate? E of 0.2. And we'll say it's 1 plus the 0.2. This will be just applying it back into the equation we got a minute ago. And we're only going to use 5 terms. Do you notice? The first one gives us the whole number. The second term is giving us the first decimal place. The third one is just giving us the second decimal place. Each one of them is sending us down further and further. What it means is, once we've even got 3 of these, there's nothing that in the following terms that's going to interfere with that amount in the answer. So we will have 1.22, and that particular thing, no matter how many more we add to it, won't change the 1.22. By adding in this extra one, we're saying, look at this new one coming in is adding nothing here or for the first 2 decimal places. When we get to the fourth one, you have 1, 2, 3, 4. It's only bringing in new numbers for the 5th decimal place. So the 5th term is giving numbers for the 5th decimal place. So every term is sending you down or one more significant figure. So it's giving you a significant improvement. Very often we only need to know numbers to a small number of decimal places. So you can see, even though we should have an infinite series here, and for pure mathematics where we need to know exactly what something is, it's important. But for us, looking for a useful answer that we can use in some calculation, 5 terms here, or even after 4 terms, what we're saying is that we're only missing out on numbers that are below the 4th decimal, the 4th zero behind the decimal point. We have 4 significant figures then of accuracy. That's pretty good. Now then, next time round we will look at the remainder, and we look in a lot of detail at the remainder of these Maclaurin series. We've looked at the easy one, and we just played around a little bit, and I've tried to keep it a little bit light because the idea is to get the concept. Once you've got the concept, you can then start to take a bit more care over exactly how you play with the numbers. And you will find that one of the great mathematicians, Leibniz, gets mentioned when we start dealing with estimating pi. And for a guy that was as smart as he was, and who is recognized along with Newton as the founding fathers of calculus, you will find that his method that he used for pi would take many thousands of terms to actually get to a reasonable value for it. And there is a small change that he didn't notice that others did spot after him that allows us within a small number of terms get several significant figures. So it just goes to show, just because somebody has a truly great idea, or even a number of them, they don't always see all of them. Okay, I'll see you next week. Bye now.